Today I want to talk to you about a problem which is actually I think one of the most interesting in all of star formation, and that is how massive stars form. So I've been working on this with a number of people, including Mark in the audience, also Andrew Cunningham, Richard Klein, Andrew Myers, Stella, and Jonathan Tam. So massive stars are really central importance in astrophysics. They form most of the heavy elements. Here's an image of the Cassiopeia A supernova remnant with different colors showing the different temperatures of the X-ray emission. This emission is entirely from newly synthesized heavy elements. The massive stars also energize the interstellar medium. The dominant heating mechanism for the cold neutral atomic gas that pervades the galaxy and also the warm neutral gas that pervades the galaxy is the photoelectric heating on dust grains. And that is produced by primarily by somewhat massive stars. Then if you look at H2 regions, the ionized gas, that's entirely produced by stars that are hot enough to produce ionizing radiation. And finally, if you look at the very hot gas in the galaxy, that's produced by stellar winds and by supernovae, again from massive stars. So here's an image of the Orion Nebula cluster, which shows the powerful effects that massive stars can have on the surrounding interstellar medium. The massive stars also govern the evolution of galaxies. So if you go back and ask, well, start up with galaxies from long ago and look at what happens as they evolve, of course, they're being constantly fed by gas from outside, but once the gas gets inside, the massive stars really dominate what happens. And one of the main things they do is with feedback, they can drive powerful outflows, as in this image here from M82, which shows the powerful outflows that are going out along the axis that are believed to be driven by radiation pressure. Question?
So my question is about how you define the massive star. How massive is a massive star here?
Okay, so for the purpose of this discussion, I'm going to define massive star as 8 solar masses because it's stars that are more massive than that can explode as type 2 supernovae. And it's at about that point that you also start getting a significant amount of far ultraviolet radiation. The median, I'm trying to remember, I think the median stellar mass for the FUV radius is like 13 solar masses. And for the ionizing radiation, that is somewhat more massive than that.
It's actually, it's like 55.
55, okay. It's also thought that perhaps massive stars may have reionized the universe. So here's a cartoon of the evolution of the universe from then till now. So here's, this is supposed to be the Big Bang. This is a few 100,000 years after the Big Bang, all the way down. We're down here at the bottom. And then the idea is that here you have the dark ages where the gas is cold, just adiabatically expanding, and then stars, and then eventually galaxies and quasars start to form, and they produce ionizing radiation, and eventually they ionize the universe, and then you can actually see through to the edge. But we are going, at least in optical light, we're going to hit this wall once you get to high enough redshift where you see the neutral atomic hydrogen. Well, why is it that we know so little about massive star formation? And there are both observational and theoretical problems. So observationally, massive stars often form in regions that are extremely highly obscured. You can have visual extinctions of 100 to even 1,000 magnitudes. Most of them, with the exception of Orion, most of them are far away, greater than a couple of kiloparsecs. And then, to make life even worse, they're extremely crowded. For example, at the center of the Orion Nebula cluster, the density of stars is like 10,000 per cubic parsec. So you really need extremely high resolution in order to be able to see what's going on. Now, theoretically, there are two classes of problems. One is that there's a wide range of space and time scales. And over the past 3 weeks, you've been hearing about this a lot. And that, of course, is one of the main reasons why the technique of adaptive mesh refinement was developed, to try to be able to start tackling this issue of the wide range of spatial scales. And then Stella described in some of her simulations where she would zoom in. So that's another way of trying to enlarge the range of spatial scales. But and the people have done truly incredible things where in some cosmological simulations you can start off with something that is the size of a megaparsec, and then you keep on zooming in until you get down to something, the first star that's forming, and the mass of the star I think was about equal to the mass of the moon. So that's the good news. The bad news is that the time step at that point had gone so small that they had to stop almost immediately. And you can imagine, I mean, basically, if you want to resolve the formation of a star and actually follow the star, we have solar oscillations, which are 5-minute oscillations. So you'd have to have a time scale which was much less than 5 minutes to follow a process that takes almost 1 million years. So that's not currently feasible. Now, the second thing that makes life complicated doing massive stars, which is unique to massive stars, and that is the importance of that radiation can actually be dynamically important. And so I'll come back to that. So the outline of my talk is I want to talk about some of the characteristics of high mass star forming regions, and then give you some of the basics. This may be overlapping some of the previous lectures that you've gotten, but I'll talk about star formation in isothermal gas and condense everything you need to know about star formation into 3 slides. Then I'll talk about some of the properties of turbulent gas, then summarize the various models for massive star formation, the challenges that are faced by these models, and particularly I'm going to focus on radiation pressure, and then some observational predictions and see how the theories are doing. So let's begin then with the characteristics of the regions of massive star formation. Oh, question?
Is magnetic field massive star forming region observed?
There is some indirect, there is, I guess, one direct observation that I'll show you a little bit later. There are observations of magnetic fields in regions which people think might form massive stars, but there's actually very little direct observation. And it's a very important question, as I'll get back to. So I've now gotten 2 questions. I think that's great. So please, anytime you have a question, feel free to ask. So here is something that was discovered. It came as a big surprise to everybody, and these are the so-called infrared dark clouds, which you can see here, this little patch of dark. So I should say what the color scheme is here. The blue and cyan colors that you can see, these little dots, those are stars. So you got a whole bunch of stars, but the green and the red, which is much smoother, that's actually dust emission. And then you see these black parts. That's where you have dust that is absorbing the background radiation. And that dust is so opaque. This image, I believe, is at about 8 microns, which is sort of a relative minimum in the dust absorption. But despite that, this dust is opaque. Now, this came as a big surprise when it was discovered by an Air Force satellite in the mid-90s. Actually, I think in retrospect, theorists should have predicted it, but that's always easy to say after the fact. Nonetheless, just as the molecular clouds, when people first started discovering them, they were kind of surprised that there were such dense structures in the interstellar medium. Now we see the insides of the molecular clouds, and people were surprised again. So here's the simulation that I described to you yesterday. This is now the whole box, and this is our attempt to try to simulate the same type of structure that you see here. And so what we did is that we essentially had took a box and drove it and allowed it first to evolve without gravity, and then we turned on gravity. And one of the things we were finding once we did turn on gravity is we were finding that these regions here, well, first of all, you see this very filamentary structure, and then these little white circles represent places where stars could form, and you can see that they're just forming right along these filaments. Now, it's thought on the basis of some evidence that these IRDCs, as they're called, are the sites of massive star formation. So before I continue, I want to clarify some terminology. And this is that there's really a hierarchical structure in star-forming regions. And on the largest scale, you have GMCs, and those are like between 100,000 and a million or a few million solar masses. Then inside the GMCs, there are gravitational, and these GMCs, I say, are by and large at least gravity is significant. It plays a significant role in their structure. There are also gravitationally bound substructures on the scale of thousands of solar masses. Those will go ahead and form clusters of stars. Then inside these clumps, there are so-called cores, which are going to form individual stars or binaries. And so there's a hierarchy of masses. And I should say that the clumps actually can have subclump structure, so it's not that there's always a hierarchy of 3. But there is this outer hierarchy is well defined because it's defined by the transition from atomic to molecular gas. So that is a very definite transition. And this core is also well defined because, like I say, it's going to form a single star or a binary. So the characteristics of the clumps that are going to form high mass stars were summarized in a very nice paper by a couple of papers from Neil Evans' group. And the sound speed is a few tenths of a kilometer per second, a little bit higher than in low mass star forming regions. The supersonically turbulent, though, the velocity dispersion, the one-dimensional velocity dispersion is almost 10 times the sound speed. The size is somewhat less than a parsec, and the mass can be several thousand solar masses. So if you work that out, that corresponds to a density of a couple 100,000, excuse me, 210 to the 5th hydrogens per cubic centimeter. And that means a surface density that corresponds to about a gram per square centimeter. So this is very strange. For those of you who've worked on interstellar medium problems, you always use numbers like number of particles per cubic centimeter. So that's a very small number by earthly standards. But if you're talking about a gram per square centimeter, that's something that you can have, drink some water, and you can, have that's a milliliter of water, and centimeters. It's amazing that you have something that we experience here on Earth is actually a unit that is relevant in the interstellar medium. And that corresponds to a very high extinction of order a couple hundred magnitudes. So if you compare that with the typical giant molecular cloud in which this clump is embedded, the average density there is more like 100, and the surface density is more like only a few hundredths of a gram per square centimeter. So there have been observations of cores inside these massive clumps. So let me start here on the right, and here is a piece of an infrared dark cloud, and then radio observations showing that there appears to be a massive core here, which has already there. I think there's a protostar in here, and it looks like it might turn into a somewhat massive one. Then on the left, there are maps or attempts to measure the spatial distribution of the gas in one of these cores, and they seem to be consistent with power laws with indices of order 1.5 or so. Now, the case that I showed, as you can see here, this is kind of an isolated structure. As I mentioned before, in massive star-forming regions, often you form the stars in highly clustered environments. And it remains to be seen whether you're going to have this core be able to identify these cores for the massive stars in those clusters. That's why the results from ALMA will be extremely exciting for that. So then, to just again give you some more terminology, an evolutionary sequence for a high mass star formation is, as the core evolves, you're going to start off with a high mass starless core, and then you get to form a protostar in there, and you can form either a low mass or intermediate mass star that's on its way to becoming a high mass star. And then you will actually get a high mass protostellar object. So then once it reaches this somewhat arbitrary dividing line of 8 solar masses, then it's going to be this. And eventually you clear away the surrounding gas and you wind up with a final star. The clump evolution goes through a similar evolution where you can, in principle, have a massive starless clump. But at least in a search in the first quadrant of the galaxy recently, John Balley's group found that there were no massive starless clumps that were more massive than 10,000 solar masses. So what this means that you already, by the time you get to at least the density threshold or the column density threshold they were using in their search, you've already started to form massive stars. Once the stars start forming, you get protoclusters, and then finally they clear away all the gas, and you wind up with a stellar cluster. So let me now do my somewhat ambitious attempt to teach you everything you need to know about star formation in just these 3 slides. And the pioneers in this work go all the way back to James Jeans, and then there's Bonner and Ebert, Richard Larson, and Frank Hsu. So first, let's work out what the characteristic timescale is. And the characteristic timescale for self-gravitating gas, you can say that you have the acceleration, and we're just going to approximate the second time derivative here, just r over t squared. And that's given by the acceleration due to gravity, gm over r squared. So if I go ahead and I solve this equation for t squared, I get r cubed over gm, and m over r cubed you recognize as the density. So basically that's of order 1 over g rho. So you can actually go ahead and calculate what is the free fall time for a pressureless sphere, and you find out that it is 3 pi over 32 g rho, and the square root of that. So in other words, we got the correct dimensional dependence on this from this very crude argument. And then this is 3 pi is about 10, so we're off by a factor of about 1.7 to get this free fall time. If you put in numbers, this is about a little over 100,000 years if you were at a density of 100,000 hydrogens per cubic centimeter. Okay, let's work out what the characteristic mass is. So what we're going to do is we want to compare the kinetic energy per unit mass with the gravitational energy per unit mass. So we define the isothermal sound speed squared as just the pressure divided by the density, and that is then a measure of the internal energy. And then we compare that with the gravitational energy per unit mass, which is just gm over r. So another way of saying this is you're just equating the isothermal sound speed squared with the escape velocity squared. Anyway, you can go ahead then and solve this equation for the mass, and you just get that as rc squared over g. So what's the characteristic radius? Well, that's just going to be equal to the sound speed times the characteristic time we already found. So we know that goes like 1 over root g rho. So here we have what the characteristic radius is. So then if we go ahead and we stick that radius in that equation, we get that we get cs cubed tff over g, stick in what we get for the free fall time, and we find that the characteristic mass is order the cube of the sound speed divided by the square root of g cubed rho. So what's the Bonner-Ebert mass is the maximum mass of a stable isothermal sphere. And that is equal to 1.18 times this answer we got up here. So this very crude dimensional analysis has already given now an answer that's accurate to 18%, which is better than you can do usually. So physically what this means is that if you have a mass that's much less than a Bonner-Ebert mass, then self-gravity is just not important in the structure of that object. And as you approach this Bonner-Ebert mass, gravity becomes more and more important. When you're at the Bonner-Ebert mass, you have a density ratio of 14.1 between the center of the sphere and the edge. And if you have any larger density contrast, in fact, it's gravitationally unstable and will collapse. Okay, so finally, on our third slide that we're going to finish up on star formation, we want to get the characteristic accretion rate. So to get the characteristic accretion rate, we take our characteristic mass and divide by a characteristic time. So that is, the mass was c cubed over the square root of g cubed rho, and then 1 over the free fall time is then you have a root g rho in the denominator, and look at what happens. The rho's cancel out. So that all you get for the accretion rate is the order c cubed over g. Well, Frank Hsu worked this out for a singular isothermal sphere, and now we've done even better. We're accurate 2.5% in this very simple-minded analysis. Now, if you go ahead and plug in numbers, you find that this is a little over 10 to the minus 6 solar masses per year at a temperature of 10 Kelvin, which is the typical temperature of cold molecular gas in the galaxy. So if you have an isothermal gas at 10 Kelvin, then it's going to take about, say, a little over 600,000 years to form a 1 solar mass star. That's actually pretty close. I think Neil Evans, if he just talked about this, I think his typical estimate is like 500,000 years for that to happen. But there's a big problem. It implies that it takes 65 million years to form a 100 solar mass star. But a 100 solar mass star only lives for 3 million years. So clearly, we have to generalize the theory. So let me now talk about what happens. What I was talking about there is isothermal gas. We didn't have any turbulence. What happens when you have turbulence? And this is now very important in the interstellar medium. And here are some of the pioneers in observation. And I want to emphasize, because I think this is really great, that the first pioneer in observation was a theorist. Richard Larson did this, looked at some of the data theoretically, and was the first one to actually find some good evidence for turbulence in the interstellar medium. Then Edith Valgrone, Phil Solomon, Phil Myers, Alyssa Goodman. And then a number of people have worked on theory, including some of the people that, like Eve Oestreicher, that you had talk here. Okay, so what I'm going to talk about then is what's called the line with size relation in turbulent gas. And what that it gives is just a relationship between the velocity dispersion and the size. And this was first worked out, a very kind of famous piece of work by Kolmogorov in 1941. And in the picture of turbulence in an incompressible medium, so if you have like turbulence in water or very subsonic turbulence here in the air, then you have essentially, and even Da Vinci, there's a famous cartoon he drew, where essentially he had large eddies, and these large eddies created smaller eddies, and then the small eddies created smaller eddies. And this picture then was formalized. And if you say that if you have a steady cascade, so I have an energy per unit mass here, that's v squared on this scale L, and then I divide it by the flow time here, this has to be a constant if I have going to have a steady state. So this flow time is just L over V, so it says that V cubed over L is a constant, or namely V goes like L to the 1/3. So this is a very famous result from, for incompressible turbulence. For compressible turbulence, you find that the velocity instead goes like the square root of L. And then if you get do fancier simulations, maybe it differs slightly from the square root, but basically it goes like the square root. And so these then are called line width size relations. And Larson, who's a theorist, as I mentioned, discovered the line width size relation in the interstellar medium. And then you could ask, well, here we're talking about this line width, and if it's supersonic, we're talking about driving supersonic turbulence. What drives that turbulence? So several suggestions have been made. One, supernovae, and that is certainly important in the diffuse interstellar medium. Star formation, a number of people have suggested that star formation could do that. And then self-gravity. And Field et al. Talked about the self-gravity in sort of in general. And then you can talk about gravitational accretion, that is actually forming GMCs by the process of accreting matter from the ambient medium, and a couple of groups, including Mark and then Nathan Goldbaum, who may be in the audience also. So here then are the observations that Edith Valgrone has summarized. You'll notice this is an unusual reference here, this 2013 question mark. That's because Edith and I started this project 3 years ago, but she's been seduced by the Planck and is now working full time on trying to analyze Planck data. So it's hard to make progress on more conventional things like this. But the interesting thing here is if you just focus on 12CO data only, so that you don't worry about things with different tracers, and then you plot the non-thermal line width as a function of the size, you see there's some dispersion, but over a huge range and scale, all the way from 1/100th of a parsec to 100 parsecs, basically you can fit that with a curve which goes like the predicted L to the 1/2. And here I put in the coefficient. There is a significant dispersion of half a dex. In other words, a factor of 3 about that. Now, earlier I showed you a picture of an infrared dark cloud. If you plot them on this graph, they really do not fit. They sit well above this line width size relation. So these high mass star forming regions then do not agree with the line width size relation that most other molecular gas seems to obey. So what's going on? Well, let's look at what the situation is. For unbound gas, the line width size relation that I just showed you is given by that. What about gravitationally bound gas? And I call this then the turbulent line width size relation. For bound gas, you have what I call the virialized line width size relation. So if you define the virial parameter, which you've probably seen before, is just defined as 5 sigma squared r over gm. So this parameter, if you have a sphere at constant density, then at this point the internal energy is half the gravitational energy for such a sphere, and that means it would be in virial equilibrium. But it's a convenient parameter. You just go ahead and measure the effects of gravity even if you don't have any of those assumptions being satisfied. So then you go ahead and write down the mass in terms of the surface density, and you see one of the r's cancel out. So then if I go ahead and I solve for the line width, I now find that the line width is not proportional not only to the square root of r, but also to the square root of the surface density. And if you assume that things are gravitationally bound so that the virial parameter here is of order unity, then you get this. So I want to contrast this 1/2 with that 1/2. This 1/2 up here in the turbulent line width size relation is derived from observation, and there are some people make measurements in some regions. You get slight differences from 1/2. This one is by definition. Well, I'm sorry, this one is by definition when I include the virial parameter. If I then make a physical assumption that this parameter is constant, I then get this by essentially by definition. So it has to go like r to the 1/2, but I have an additional dependence here on the surface density. And if I plug in the numbers to bring it into the same units here where I get the full width half max, then it's about the same numbers, a little bit less, 0.9 kilometers per second, if the surface density is the order 100 solar masses per square parsec. Okay, so now what I can do is I can go ahead and I'm going to divide out the L to the 1/2. So let me go back to this graph. Oops, takes a while. Here I plotted the line width against the size, and we said that it went like the size to the 1/2. So I'm going to divide out that size to the 1/2 and plot it as a function of surface density. So what you find is that there are two regions. There's a region where you have the turbulent line width size relation for unbound gas, and in that case the line width is independent of the surface density. But when you get to higher surface densities, then it starts becoming dependent on the surface density, and it's consistent with roughly the square root of that. So you have, and the interesting thing is that GMCs lie right in the middle. So GMCs then are both, the way I like to think about this is that they're feeling the effects of the ambient interstellar medium. So their properties do depend upon the ambient medium. And then when I go inside the GMCs here into denser structures, they're actually insulated from the interstellar medium. Their pressure is really determined by what's going on in the overlying molecular material. And in terms of what kind of objects we're talking about, these are the high latitude molecular clouds. So some of these things, for example, Stella showed you a picture of the Polaris flare, and some of these objects, I think, come from here, and these are the high mass star forming regions. So now, how does high mass star formation differ from low mass star formation? There are a number of differences. The first is that the protostellar core can contain many Jeans masses. So for low mass star formation, we estimated the characteristic mass, that was the Bonner-Ebert mass, and that was a solar mass for typical interstellar conditions. And that does you well for low mass stars. If I'm going to make a 100 solar mass star, if I had 100 solar mass, well actually it's not completely efficient, so maybe I need a 300 solar mass core to make a 100 solar mass star, I'm going to have a lot of these Jeans masses in it. So that's an important difference. Correspondingly, we just saw that the turbulent line width increases, the turbulent velocity dispersion increases with scale. So if I have a much bigger core, I'm likely to have turbulence in the core that's going to form this massive star. This gets back to the earlier question about the role of magnetic fields. It's possible that they are less important, and this is going to be something important to try to measure. So yesterday I described to you Crutcher's work on summarizing the magnetic fields. If you go ahead and put in his result for the maximum magnetic field, you then find that the magnetic critical mass, which remember, that's the mass where magnetic fields basically can balance the effects of gravity. So once you get bigger than that magnetic critical mass, then that means gravity wins. And this maximum critical mass is depending upon which of Crutcher's results you use, is like of order 4 to 30 solar masses, and then with a weak dependence here on the density. And as I said, if I want to make a really big star, I might have to have a core that's more than 100 solar masses. So in that case, the magnetic field might definitely be less. Okay, the next thing is that radiative feedback can be significant. And this was realized decades ago, first by Franz Kahn, and then in a classic paper by Larson and Starfield. And the force due to the radiation pressure can exceed that due to the gravity. That's really a basic problem, and I'm going to spend some time talking about that. Another thing that can happen is that the protostellar accretion can continue after the star reaches the main sequence. So if you look at a low mass star, the Kelvin-Helmholtz time, that is the time for the star to go ahead and readjust its structure based on allowing energy to escape, is much longer than the star formation time. But that inequality gets reversed for high mass stars, so that you actually can form the star faster than the star can radiate its energy. I'm sorry, it's the other way. I misspoke. For the low mass star, the star forms faster than you can radiate away the energy, whereas for the high mass star, the reverse is true. The star is forming so rapidly that it can radiate energy so efficiently because the luminosity is high that it can actually get to the main sequence and while you're still accreting. And that becomes particularly problematic once you have a star that's producing ionizing radiation. Nonetheless, despite this long list of differences between high mass and low mass star formation, there's still a very interesting question. Can you model high mass star formation as basically just a scaled up version of low mass star formation? So the theories of star formation that have been advanced so far are a general class of so-called core accretion models, in which you imagine that there is a gaseous core that has a mass somewhat bigger than that of the star, and then it's going to go ahead and form one or just a few stars. And that's, I think, well validated for low mass star formation. The question is whether it works for high mass star formation. Then I'll just mention the particular version. In fact, it's the version that's been worked out in greatest detail for these models, the turbulent core model, and talk about an important problem that you come up with in that model, which is suppressing fragmentation. The main other model is so-called competitive accretion model, so I'll discuss that. And finally, the most innovative model is the stellar collision model. So let's now begin with the core accretion model. So the basic idea is that if you have a molecular cloud, that you can actually go ahead and identify regions in this cloud which have masses somewhat greater than the mass of the star that's going to form, and that each of these regions then is going to collapse and form one or perhaps a few stars. And so that makes a very strong prediction. That predicts that the initial mass function of stars is determined by the core mass function in the molecular cloud. And this, in fact, there's been a lot of activity in the past decade on theories of the initial mass function. And this is the basic assumption that these theories make. That is, you go ahead and you can calculate the distribution of clumps. In fact, people actually even turn off gravity and go ahead and do a turbulent simulation, and then you can see what the mass distribution of the clumps is, and then you say that you're going to essentially form stars by that. And the challenges faced by this are that one I mentioned before: why doesn't the core fragment into small stars? If I go ahead and I have this core here, say it's 100 solar masses, and if the Bonner-Ebert mass is 1 solar mass, why doesn't it make 100 1 solar mass stars? Where are the protostellar accretion disks? Until recently, there was very little evidence for any protostellar accretion disk. That's a very common feature, in fact, ubiquitous feature for low mass star formation. Where are they around high mass stars? So then I'll just talk about the particular model, core accretion model that I developed with Jonathan Tan. And what we did was this, again, a very direct a generalization of the model that I described to you that Frank Hsu developed for isothermal gas. And that is simply to say that instead of saying that I'm going to put the cube of the sound speed here, I'm instead going to put the cube of the velocity dispersion here. Now, the problem is that whereas when Frank was doing his isothermal model, he knew what the sound speed was. He could look, or he didn't, but observers looked and they told him that the temperature was about 10 degrees, so he knew the sound speed was about 0.2 of a kilometer per second, so he stuck that in, and he knew how what the accretion rate was. But we don't know what this is because it's highly supersonic, and we have to determine that self-consistently. So what we did was we just used the virial equilibrium, so that says sigma squared is order gm over r. And then if you just use the definition of the surface density here, you can go ahead and express this accretion rate, sigma cubed over g, in terms of the mass and the surface density. And so this is the mass of the core, and this is the surface density of the core, and we argued that that was about the same as the surface density of the clump in which it was embedded. So basically then, the accretion rate is determined by the core mass and by the surface density, and you would get high accretion rates if you are in a region that has a high surface density. Now, turbulent cores are scale-free, and so we modeled them as singular polytropic spheres. So a polytrope is just where you have the pressure going as some power of the density, and so if you don't have any scales, then you necessarily get something like that. And the theory for those had been worked out earlier by McLaughlin and Pudris. So if you go ahead and numerically evaluate the result that we got, then we got that massive stars form in about 100,000 years. Here I have it, it's 50,000 years for a star that is going to wind up being 30 solar masses. And here's the dependence on the surface density of the clump in which it's forming. Okay, but now there is this problem about fragmentation. How can we avoid that? If I'm going to form a star of 30 solar mass, I might need a core that's going to be 60 or 100 solar masses, and the rest is going to be ejected by the outflow that's associated with the newly formed star. But the maximum mass that I've said is around 1 solar mass, and so then this question that was first asked almost a decade ago by Claire Dobbs and collaborators: why doesn't this core fragment into like 100 small stars instead of one large one? And the answer is that the high luminosity of the accreting protostars actually raises the temperature of the gas to several hundred Kelvin within 1,000 AU. And so that significantly increases the Jeans mass and suppresses fragmentation. So Mark was the first to show this analytically, and then we subsequently showed it numerically as well. No fragmentation. We don't get any fragmentation when we in our calculation. So I think that this thermal feedback from the newly formed stars then can resolve that issue. So now let me go on to the second class of theories. That's so-called competitive accretion. And so the idea there is that massive stars form by Bondi-Hoyle accretion. So Bondi accretion is when if I take a star and I stick it in a uniform medium and it's stationary, then the gravitational attraction of the star will cause gas to flow onto it. That's called Bondi accretion. If I now allow the star to move, then Hoyle contributed to the solution of that problem, so that's called Bondi-Hoyle accretion. And then if you say that you actually, you're not an infinite uniform medium, but there are tidal gravitational fields, that modifies it. And Bonnell and company showed that best describes what happens in their simulations. So they then use simulations, and they find that the stars form, low mass stars form the same way that they usually do their cores, and they collapse. But once they form, the stars are moving around, and but slowly, and gas is flowing in, and the stars just accrete this gas by Bondi-Hoyle accretion. So I think I mentioned yesterday, and I'll repeat, that there's a very key difference between the initial setup in the simulations that get competitive accretion and the setup that we use in our calculations. And that is, and these simulations start off with very smooth initial density profiles, and therefore you do not have an initial clumpy structure, and it then tends to lead to a different outcome. The challenges for this theory are that, first of all, it does not work in a turbulent medium. Actually, Bennell realized this in the first paper that they wrote. They described it as having the motion of the stars. If the stars moved and had virial motions, then they would be moving too fast and the Bondi-Hoyle accretion rate goes down. With Mark Krumholtz, Richard Klein and I showed that if you just put a star in a turbulent medium, the accretion rate is much too small for it to work. So you somehow have to suppress the turbulence. Then more recently we've shown that magnetic fields reduce the rate of Bondi-Hoyle accretion, and wide-angle outflows will reduce the accretion, but in fact neither of these effects have been included in the simulations. Now, in both the first theory I mentioned, the core accretion models, and then also this one, there's this problem of radiation pressure. Why doesn't the radiation pressure just halt the accretion altogether? Okay, finally I'm going to give you the, briefly describe the third class of theories, and that is the stellar collision model. Once again, Ian Bennell was involved in developing this model as well. And in order to overcome the problem that I just mentioned of radiation pressure, they said, well, what happens if you form a cluster, and the cluster of stars is so dense that the stars actually physically collide with each other? Then radiation pressure is totally irrelevant. And then there was a state of magic that occurred in which you would have these very dense star clusters where stars are actually bashing into each other, and then a miracle occurred and they would expand, and you would get the clusters we see where stars don't collide. So as you can see from that comment, I never believed it. But anyway, I should say that recently there has been very interesting work, both observational and theoretical, on stellar collisions that occur after the stars have formed. And in fact, in this paper by Sana et al., they showed that a significant fraction of massive stars may actually undergo a merger during their evolution. Then Mokel and Bennell worked out a theory for if you have triple star systems, that it's possible for some of them to induce mergers. And then Fuji and Portuguese Svart looked at the hierarchical clusters and showed that in that case you could also get some stars to merge. So the very most massive stars that are observed, in fact, could be the result of such stellar mergers. Now, recently it has been possible to carry out simulations in which they include both the n-body effects and also in the direct stellar collisions with the gas. And in this case, there have been two papers that were published a couple of years ago, and they showed that the stellar collisions are not important in forming either sort of a normal cluster like the Orion Nebula cluster, or even the more extreme cluster like the Arches cluster, which is near the galactic center. Okay, so I've mentioned several times that a fundamental problem in star formation is radiation pressure. And let's look at that. So the force due to the radiation pressure is proportional to the flux, which is just L over 4 pi r squared. And the force then is this flux times the cross-section divided by the speed of light. And if I plug that in, I get this expression here. So you then define the Eddington luminosity. The Eddington luminosity is often used in discussion of binary X-ray sources, supernovae, and so forth, where you have very powerful source of radiation, and you're thinking about the Thomson scattering of the electrons. But it works equally well for high mass star formation, where you're worried about the force of radiation on dust. So that Eddington luminosity is when the radiative forces balances gravity. And if we just use this expression for the radiative force, but now this is the Eddington luminosity, we equate it to the force acting on a particle of the mean mass mu, and that gives you the Eddington luminosity, which is directly proportional to the mass of the object. So typically the cross sections per unit mass for dust in the massive star forming regions is of order, say, 5 centimeters squared per gram. Plugging that in, you find that the Eddington luminosity is around 2,500 solar luminosities at 1 solar mass, and it scales linearly with the mass. So now massive stars are very luminous. In the region we're going to be interested in, between 7 and 20 solar masses, it goes like the cube of the mass. And then but it then flattens out a little bit. So instead of having this scale all the way up to 100 solar mass, by the time you get to 100, you're at 10 to the 6th instead of 10 to the 7th, which the other equation would give you. So now we predict that the protostar, this is one thing that's great about theory, right? You do very simple arguments like I'm doing here, and we're going to come up with a very powerful prediction. Because obviously, once the radiation pressure exceeds the gravity, then it's going to stop accreting. And you can now solve this. We set L, we know what it is, and if it's greater than the Eddington limit, then we can solve for the mass. And you conclude that the most massive star that exists in the universe is 16 solar masses. But there's a problem. We observe stars that are more massive than 100 solar masses. How is that possible? So, and this is a case when the simple-minded theory is catastrophically wrong. So, people have been thinking about this for a long time, and one of the first points that was made was, what about the effect of accretion disks? So, because the accreting gas has some angular momentum, it will form into a disk before it goes directly to the star. This was, of course, long before people worried about the effects of magnetic fields, which I discussed yesterday. And people then showed that this disk would produce a shadow, and because it shadowed a lot of the gas, then you could continue accreting. And so here are some of the works that were done on that more than a decade ago. So then we carried out the first 3D simulation of massive star formation that included this radiation pressure, and we concluded that Rayleigh-Taylor instabilities were very significant in allowing the massive stars to form. And then we also then worked out what the effects of bipolar outflows were on this radiation pressure. So I'll talk about that in a little more detail. So here is the collapse of a 100 solar mass core to a binary, and we're going to form a binary that has a mass of 39 and 27 solar masses. So on the top two panels, this is on a big scale of 1/4 of a parsec. Down here, I have the small scale. We zoomed in to 2000 AU, which is 1% of a parsec. And then this column is the column density, and this along the axis, and this is then going to be the density in the plane with the axis. So here I have column density, and I'm essentially looking down on the formation. Here I'm looking from the side, and I'm doing the density. And let me see if this will, is it, there we go. Okay. So as time goes on here, you can see the collapse, and we have a mark, this object here indicates you have a protostar forming, and you can see it spinning around faster and faster, and then you blow a large bubble. The radiation pressure is actually blowing the gas out. But then you see what happens is that the gas is able to start falling in nonetheless. And we attributed this to Rayleigh-Taylor instability. So at the top panel on the large scale, you can see that these fingers, Rayleigh-Taylor fingers, are going out to very large distances. Okay, so the conclusion of our simulation was that the combination of the Rayleigh-Taylor instability and disk formation allowed the massive star to form. But I have to say that this work that we did on the Rayleigh-Taylor instability has been called into question. Now, we found that it was effective. Mark then worked with a student and did some analytic work, and again concluded that the Rayleigh-Taylor was effective, and an independent simulation by Zhang et al. Also finds that. However, Kuiper and collaborators wrote a paper in which they concluded the opposite. So each of us has criticism of the other's work. We're in the process of doing a better, more accurate simulation, and we will resolve the issue, we hope. Okay, now the other thing I mentioned was that protostellar outflows can help reduce the radiation pressure. How can that happen? Well, protostars have the very powerful outflows, and these are mainly observed for low mass stars. The mass ejection rate is like 10 to 30% of the accretion rate, and the wind velocity, or jet velocity, is of order the Keplerian velocity at the surface of the star. And it's believed that these, and there's good evidence that these outflows are driven by magnetic forces associated with a rotating magnetized disk. So here's some famous pictures from Hubble of some of these outflows from low mass stars. And this, the length bar here, that's 1,000 AU. So in this one down here, this is 1,000 AU here. You can see that this now is getting, so that 2,000 AU is 1% of a parsec, but so this is quite big. Now, I mentioned also in answer to a question that there is some direct evidence for outflows from massive stars. Here is an image where we have 6 centimeter continuums. That's from synchrotron radiation, and that maps out an outflow. Here, the grayscale gives you the thermal emission being heated up from a star. The total luminosity is about 17,000 solar luminosities, and that's due to one star, and that corresponds to about 10 solar masses. So that provides direct observational evidence for such outflows. So the wind cavity then that's formed by these outflows can channel the radiation away, and that reduces the radiation pressure. So here is a simulation that we did that is forming an entire cluster of stars. It's meant to be somewhat similar to the Orion Nebula cluster, and we included the outflows. Unfortunately, in this particular simulation, if I can get it to work here, you're not going to be able to, the outflows don't stand out. But as time goes, on the right, you see the temperature, and you can see the different stars forming, and it's lighting up the region. In the left is just the density, and you can see the stars that have formed on this filament. So this simulation was the first one that was able to actually produce the IMF with massive stars. Stella showed you a number of simulations that have produced the IMF. They always, and it is discouraging that everybody always gets the IMF even if they don't include all the physics. But this was the first one to actually get up to more massive stars, where you have to include the radiative feedback. And I should say the results are also consistent with core accretion models. So here's the comparison of the theory that I described earlier with simulation. And we have the 4 most massive stars, how they're growing in mass as a function of time. And here is the prediction due to the core accretion model. And you can see that it's the turbulent core model, I should say, and you can see that it's quite good. So the conclusion on the radiation pressure is that indeed the outward force due to radiation pressure can exceed the inward force due to gravity during the formation of massive stars. But geometrical effects that are associated with the disks and the outflow cavities reduce the effect of the radiation pressure. So the disks provide shielding, and the outflow cavities allow the radiation to escape. So they also cool the gas, which increases fragmentation. And we found that radiative Taylor instabilities can allow continued accretion onto the star. And in fact, for the simulation we run, there's no evidence that the radiation pressure can affect the final stellar mass. So that actually then leaves open the question. It's really not known whether the maximum mass that stars have, which is believed to be of order 120 to 150 solar masses, is set by the physics that I've been talking about here, or it could be that it's due to stellar physics, that is, that stars become intrinsically unstable once they become more massive than that. So what are the observational predictions? First, the massive stars form in cores that have surface densities with of order 1 gram per square centimeter. So in the paper that Jonathan and I wrote in describing the turbulent core model, we assembled these data, and what we did was we had both star-forming clumps and then various star clusters. We had the mass, the half-light radius for the clusters, and then the surface density. And what we, as I said before, for the star-forming clumps in the Plume et al. Paper, the typical surface density was ordered 1 gram per square centimeter. You then go ahead and evaluate this for different kinds of clusters, like the Orion Nebula cluster was like 1/4 of a gram per square centimeter. For the Arches cluster, it's about 4 grams per square centimeter. If you take the median globular cluster, it's very close to 1 gram per square centimeter. And then in extragalactic clusters, you can get somewhat higher, and in fact, in this case, then you get even much higher. So the prediction is that then, as more work is done, that they will continue to find that the surface densities are very high. Okay, The next prediction is that the IMF should follow the core mass function scaled down by a factor of a few. And Chris Matzner and I argued this in the paper that Stella referred to earlier, and it's also then implicit in the work I did with Jonathan Tan. So, in fact, observationally for low mass stars, you may have seen this earlier, this is one of the most famous graphs in star formation because it shows this very clear relationship between the D here's for dark core mass function and here's the IMF. Now, I have to be honest with you, this is a very, looks like it completely proves my point. First of all, it doesn't go to very high masses, so we don't really, this really remains to be shown that it continues to work. The second point is most of the cores in here are not self-gravitating. So it's not as good an example as you would ideally want. There are some other examples people have found also where at least they are self-gravitating. Now, this then is going to be very important for ALMA. Stella talked about being able to determine the binary structure, but even before that, to just try to get the core structure in these very dense regions is going to be a very powerful test of this core accretion model. Okay, the third prediction is that massive disks should accompany these massive protostars. And that's in contrast with competitive accretion, because remember, you just have this star kind of like a little Pac-Man going through the gas, eating up gas. And so sometimes gas will fall in one way, sometimes it'll fall in another way. So it's not that you'll have no disk, but you will not have a massive disk. And in stellar coalescence models, you're certainly not going to have a disk. So in our simulations, we find that we do get massive disks, and that the disk mass can be some fraction of the mass of the star, a significant fraction. In fact, is sufficiently massive so that you get gravitational instabilities. These instabilities are very effective in actually causing the gas to accrete onto the star. And in fact, in some cases, the disk is massive enough so that you get star formation in the disk itself. Now, this to show what might eventually be possible with ALMA, we did this simulation long before Stella's much more sophisticated simulations of data, and we looked or tried to predict what you would see with if you made an observation at methyl cyanide, which is at 220 gigahertz, and so if you remember, I said there's a massive disk. We're actually looking edge-on at this massive disk. So this is not, a nice orderly Keplerian disk. And there's going to be a huge amount of information. So if you go ahead and actually then do this by the velocity slices, you can see that this picture that I showed you before, which is the integrated one, when you break it up into different velocities, then you get all kinds of structure. When the observers actually go ahead and obtain data like this, it's going to be very interesting to then try to deconvolve it and figure out what's going on. Now, one of the major advances that has occurred in the last few years is that disks have been discovered around massive stars. So that addresses one of the questions that I raised about core accretion models earlier. So here is an observation from the Very Large Telescope using interferometry. So this scale here, down here, that's 600,000 AU, that's 3 parsecs. And then they zoom in, so this is half a parsec here, and then they zoom in, and this, in both cases here, it's 20 AU. So they really, it's been truly amazing at the resolution that they're able to get. And they infer that there's an 18 solar mass star here, and there's a flared disk that has a comparable mass and extends out to 100 AU. Another thing that's been done, which is really has great potential, because I should say that this is an image of a disk, so it tells you what's there, but we actually know nothing about the kinematics. We don't know if it's a Keplerian disk at all. The second technique directly addresses the issue of the velocity structure of the disk. So this looks at infrared CO emission, and these objects are believed to still be accreting, and they had what's something called the red MSX survey. So this MSX survey was the one that found the IRDCs, and then they picked out objects a certain way based on their colors, and which they just shortened to call them red. And 25% of the sample show CO emission coming from the disk. And because this is infrared emission, it's not, you can't confuse it with the CO lines that Stella was talking about earlier. All the spectra are consistent with Keplerian disks, and they're mostly located near the dust sublimation radius. And so here is an example spectrum, and this is now a star that is 57 solar masses, so it's really huge. And you can see that you get very detailed. So I believe that the black is the data and the red is the model, and you can see that you have a lot of structure here, and the model does very well in explaining the data. So this is very strong evidence for Keplerian accretion disks around massive protostars. So now let me get to my conclusions. We said that massive stars form in regions of high surface density, of order of gram per square centimeter, that are self-gravitating, and they obey the virialized line-width size relation. The observations are consistent with the formation of massive stars via a process similar to that of low-mass stars, which leads to disk and hydromagnetic outflows, but including turbulence. And in the turbulent core model, the characteristic star formation time for massive stars is of order 100,000 years, which is then significantly less than that for the typical formation time of a low-mass star. Radiation pressure would stop spherically symmetric accretion for a mass greater than about 20 solar masses, but the continued accretion is enabled by disks, Rayleigh-Taylor instabilities, and outflows. However, I don't want to give you the impression that the problem is solved. That's really a wide open problem now, and the full understanding of massive star formation is going to require more observation, simulation, and theory, which is good for you. So the future, I think, in the near future is going to be revolutionary. ALMA is already producing extremely exciting data. And as I mentioned before, being able to get the high resolution so that you can see whether these regions that are less than a parsec in size, off at a few kiloparsecs away, whether they actually have cores that are with central massive stars in them will be very impressive. Then in simulations, we'll include all the relevant physics. If I just summarize some of the simulations in the last few years, we did one that included turbulence, radiation pressure, and protostellar outflows, but we didn't have any ionization and no magnetic fields. Now, in a current work with Andrew Myers, we were at least including the magnetic fields, but we still don't have the ionizing radiation. Peters and company included ionization, but they did not have radiation pressure, nor did they have protostellar outflows, initial turbulence, or magnetic fields. Wang et al. Included turbulence, outflows, and magnetic fields, but no radiation pressure or ionization. So you can see that we're like the blind man with the elephant, and we're all trying to get different pieces of it. But the point is, all these different groups are working on including all the physics, and in a few years, I think it will be there. So our understanding of massive star formation, I think, is going to be transformed in the next few years. And the good thing is for you that you can be a part of it. Thank you. Yeah, Joel?
I have two related questions. So one has to do with the dust that you say is the main way that the radiation pressure couples with the surrounding material. Up close to the star is generating a lot of UV radiation. The dust isn't going to live very long. So I wonder if people have been taking into account the transformation of dust. And a related question, you showed beautiful pictures of the Orion Nebula, and you pointed out that the structure of things like this is obviously largely reflecting the radiation from those O stars. To what extent have simulations actually managed to produce things that really look like star-forming regions? Not just up close to the stars, but the whole environment.
So let me address the first question on the dust sublimation. That occurs up to distances of order like 10 AU or so, and that which is on a very small scale compared to the simulations that we've been doing. There recently was some work by Hal York and collaborators where they included, actually zoomed in a two-dimensional calculation where that's easier to do, and showed that there are some effects of that. But the radiation pressure was I was talking about is acting on a larger scale. Now I should say one thing that we're trying to address with Anna here, and that is that The only radiation pressure we included was the radiation pressure due to the infrared radiation. In fact, the star, as you were pointing out, emits ultraviolet radiation, and that radiation goes out directly and interacts with a much higher cross-section than 5 centimeters squared per gram, and then gets down converted into the infrared. So we have not included that direct radiation pressure yet, but Anna's going to do it and solve the problem. Now, as to trying to get some nice pictures, I should say that we haven't produced, I don't have an example that I could do like Stella, where I could show you, 2 maps and say which one is Orion and which one is a simulation, because they differ a lot. I should say that people who do not bother with forming the star, but actually then go ahead and put in the star and look at the formation of the H2 region. I have seen a talk where someone put up a simulation and a map, and I really couldn't tell the difference as to which was which. So we're making progress. We're not there yet. Yes?
One of the studies you mentioned, so you reproduce the high mass and the high mass. We also look in that study. We also look at the binary statistics for those stars.
Well, the number of stars we formed was not really very large to do any detailed analysis of that. What we did find is that as you look as a function of mass, the fraction of binaries increases, and that was true. In the calculation that Andrew Myers is doing, which now includes magnetic fields, he is looking at this binary multiplicity, and he does, again, get qualitative agreement with the observations as to how the agreement is not very quantitative, at least yet.
We did do a quantitative comparison.
Oh, okay.
It's the fraction of binaries versus primary mass, and that agreed very well with the observations in the Hydra calculation. We couldn't do anything more detailed, like the distribution of semi-major axes or anything like that, because we didn't have the statistics.
Yeah.
But certainly the 0 to 30 thing, how likely is it that stars are member of a binary match?
Yeah, thanks, Mark. Yeah, these in the one that I looked at more recently with Andrew, there is the agreement is not so good in the intermediate, around the solar mass, but qualitatively it's doing very well. Yes.
Another question: how important is the role of high mass star formation in reionization? Are they the main driver, or?
Well, that's still a question that's under very active debate. And one of the issues is that a lot of the, these massive stars, for the population 3 stars, it's not clear that there were enough of them. People debate about whether there were enough of them to do that. If you then get into the first generation of stars that formed in galaxies, there's the question of what are the properties of those very early galaxies and what the star formation rate. People are measuring this. As far as I can tell, and Joel probably knows better than I, but I think that the massive stars are the most likely. The alternative possibilities are AGN, but they, I think, are probably too rare at that high redshift to do it. So Joel, do you have any comments?
Well, if you look at the AGM, we actually observed output from the peaks at redshifts 2 to 3, and has fallen off to infinitesimally small amounts at the redshifts where reionization occurs. So if it's AGN, they have to be a completely different kind of object. Basically, if there were POP3s that were abundant and they ended up with remnants of order 100 solar masses, then those could be mini AGN. And if they're abundant enough, well, who knows? I think the other crucial issue is the escape fraction from those early galaxies. If the escape fraction, and basically what one does in order to reionize the universe consistent with the observations of the Peterson effect and the Powell from now on, you basically have to trade off the escape fraction. Of course, you assume that sort of standard IMF, so you have enough high mass stars to make ionizing radiation. Then you've got to trade off the escape fraction and the slope of the the luminosity function or the mass function of these early galaxies in the faint end, far beyond where we actually observe it. Now, where we observe it, it's quite steep, like 1.8. And if it's 1.8, then an escape fraction of 10 to 20%, you can reionize the universe just fine.
Mm-hmm.
So the crucial questions are, what are the escape fractions? And the simulations typically get quite low escape fractions, like 5% or less, in which case you need to have a very steep mass function, probably steeper than any extrapolation of the observations indicate. On the other hand, it should be possible, especially if this redshifted light will be infrared today, and with sufficiently deep observations, we should be able to see it quite clearly. And so that's where James Webb Space Telescope is going to open a whole new window.
Mm-hmm. Yeah, thanks. So any more questions? Oh, okay, thanks.
Let us break for lunch.